A shrimp smaller than your thumb snaps its claw and creates a flash of light hotter than the surface of the sun. Not a metaphor. Not an approximation. The plasma inside that bubble hits around 8,000 degrees Fahrenheit, and it happens in less than 1 millisecond. That's not a weapon built in a lab. That's a crustacean doing it with anatomy. And the moment you understand how, you realize that some of the most violent physics in the universe is happening right now in shallow ocean water, completely invisible to us. Let's talk about what's actually going on. The pistol shrimp, Alpheus heterochelys if you want the full name, has one claw that's dramatically oversized. Not just big, disproportionately, almost comically large. When that claw snaps shut, it doesn't crush prey directly. It does something far stranger. The snap happens so fast, in under 1 millisecond, that it creates a jet of water moving at over 60 miles per hour. That's not the wild part. Here's the wild part. That water jet drops the local pressure so dramatically that the water itself stops being liquid. Water boils at 212 degrees Fahrenheit at sea level. But pressure controls boiling, not just temperature. Drop the pressure low enough and water boils at room temperature. At the tip of that shrimp's claw, the pressure collapses so hard that the ocean water vaporizes into a bubble, a cavitation bubble, without any heat being added at all. Think about that. The water doesn't need to be hot. It just needs to be under low enough pressure. And for a fraction of a second, the shrimp creates that condition from pure mechanical force. Now here is where it gets genuinely unhinged. That bubble doesn't stay. It can't. The surrounding water pressure immediately crushes it back inward. And when a bubble collapses, it doesn't just disappear quietly. It implodes. The energy that was spread across an entire cavity of vapor gets compressed into a point so small, so fast, that temperatures spike to those solar surface levels. We're talking around 8,000 degrees inside a structure the size of a millimeter. That implosion also releases a shockwave, a literal pressure wave ripping through water. The sound it produces is measured at around 210 decibels at the source. For reference, a jet engine at close range is around 140 decibels. A gunshot is about 160. This shrimp, this animal that fits on a spoon, produces sound that would rupture your organs if you were close enough to experience it at full intensity in air. The light that flashes during the collapse has its own name, sonoluminescence. Scientists still don't fully agree on the exact mechanism. That should tell you something. A shrimp is producing a physical phenomenon that we haven't completely solved yet. If this just broke something in your brain, subscribe. We cover the science that textbooks bury in the appendix and then never explain why it matters. Now here's the second layer that makes this even stranger. Pistol shrimps are not rare. There are over 600 species of them. They live in coral reefs, in shallow coastal water, in places you could snorkel. And when you get many of them together, the collective snapping is so loud that it creates a background noise across entire regions of the ocean that interferes with submarine sonar. The U.S. Navy had to account for pistol shrimp colonies during World War II because their snapping was masking the sound of enemy submarines. Hundreds of tiny shrimp, armed with cavitation physics, accidentally defeating military technology. But zoom out further. Cavitation isn't just a shrimp trick. It's a problem and a tool across all of engineering. Ship propellers cavitate and destroy themselves from the inside out. The same collapse mechanism that the shrimp uses offensively literally eats metal over time. Hydraulic pumps fail from it. Turbine blades erode because of it. Engineers have spent decades trying to control the thing a shrimp evolved to weaponize. And now researchers are looking at that shrimp claw as a blueprint. The geometry of the claw, the way it channels and accelerates that water jet, is being studied for everything from medical ultrasound targeting to needle-free drug injection systems. The idea is simple. If you can create a precisely aimed cavitation event, you can destroy a kidney stone or punch a drug molecule through skin, without any incision. A shrimp claw is being reverse engineered for surgery. What I want you to sit with is the scale of this. We are not talking about a large, exotic creature in the deep ocean doing something we'd never encounter. We are talking about an animal small enough to hold between 2 fingers, living in reefs that tourists swim over every single day, operating physics that involves plasma temperatures, supersonic water jets, and light emission from collapsing gas, and doing all of it with a body part it grew naturally. Evolution had no physicist guiding it, no engineer drawing blueprints. It arrived at a mechanism so extreme that it produces conditions we associate with stars. And here's the question that should be keeping you up at night. If something this small can reach those temperatures and pressures through pure mechanical geometry, what other extreme physics is hiding inside biology that we simply haven't looked at closely enough yet? The pistol shrimp didn't evolve to be impressive. It evolved to eat. The physics was just a side effect. The universe does not care what scale something operates at. The same equations that describe the sun's corona apply to a bubble the size of a grain of sand collapsing in a reef in the Caribbean. That is either the most terrifying thing you've heard today, or the most beautiful. Maybe both. If you want more science that sounds like it should be science fiction but isn't, subscribe and hit the bell. Next video, we're going into something that makes the pistol shrimp look gentle. You won't want to miss it.